probably I set that problem up, and I'll tell you the answer, and I'll tell you the steps. You know, look at it, you can see my pain. So let's try to better. Well, is this the start of week 3? Is that right? Mm-hmm. We're still here so far. The football team postponed game. It's kind of a bummer. Haven't kicked us out yet. How are you doing, Christina?
Pretty good.
Doing all right?
Yeah.
The decision to come to grad school still a good one? 3 weeks in? No?
So far.
So far? Yeah, it's okay. So does it feel different than undergrad, or does it feel the same still?
Sort of the same still.
Sort of the same. Have you worked out your advisor stuff yet? Do you know who you're working for, or who you think you're working for?
Yes, but I haven't actually talked to any other professors yet.
Okay, so you think you've got your one figured out. We've got to kind of do a breadth of stuff, talk to some other people.
I've only been working on the project, so.
Are you working with Dean? Is that who you're working with?
Dr. Baxter.
Dr. Baxter. Cool. So which project are you doing with him? I know he has a funny project.
The tritium.
Okay, the tritium. Okay. There's so many people on these nuclear kind of projects. Guess that's where the money is. You know, it might be.
Oh, sure.
Begging for a writing utensil?
Yeah, I have my backpack, but I don't like carrying everything all day, so I just swapped and I forgot to swap my writing utensil.
All right, well, we're missing a couple today. Yeah. Zach, mechanical engineer. But maybe we can get started with the prayer. Have anybody who's willing to do that for us? Dan, please.
Our dear Heavenly Father, we are very grateful for the opportunity we have this morning to get and discuss more about transport phenomena. We ask for the Spirit to be with us, that we'll be able to better comprehend these concepts, and as He bless Dr. Judy, he'll be able to share the things he's prepared. We're grateful to him for the sacrifice of that prayer. We're grateful for our help and ask a continual blessing. We'll be able to stay safe and loved ones as well. For these things we ask in the name of thy Son, Jesus Christ. Amen.
Amen. Thank you. All right, so I wanted to real quick, you guys get my email about the advisor selection form? Everybody get that? So Zach's like, no, I didn't, but right, when you come to grad school? Okay. That was this head went down taking that as confirmation. So, so we got that out, and October 1st for that turn in. So if you have any questions, that would be a great time.
What happens if we don't talk to 6 people and talk to like 5 or 4?
If you don't talk to 6 people, I don't know what's the consequence of not following directions at graduate school. Getting fired? I don't know. I guess you should talk to 6 people, but I don't know if we've thought through consequences. That's kind of an undergrad question, isn't it? What is that? What's the consequences if I don't do this? Like, what's the consequences if you make your boss grumpy? They think a little bit less of you, right? That's kind of the consequence, I think. They were like, he didn't follow directions. That's how he's so grumpy. Let's see. That's an okay question, I guess. Kind of poking you a little bit. All right. Any other questions? Okay, I'll just reiterate. So it sounds like I've talked to a few of you. I think a bunch of you have people that you're already connected with. Make sure you just talk with a couple extra other folks. I think the only wants you to talk to 6. That way, you have people that you know who to put on your committee. You might talk to someone and think, oh, I want them on my committee. Then you might talk to your advisor and they might tell you, oh, I already have them on 3 other committees. We maybe need to branch out. So it's good to have a couple other people to talk to. And then make sure if you've been unsure through this process, if you're still finding someone, make sure you talk to your person that you're really interested in working for at least once, and that they know that you're really interested, right? We don't want surprises at the last minute. We've had that in the past a couple times. Someone puts someone down and that professor doesn't even turn in a sheet because they don't think they're taking someone or something else. So just make sure that you talk to people. Yeah.
When you form a committee, does it have to be professors from here? Does it have to be
That's a great question.
people with a PhD? Like,
Yeah, that's a great question. So they generally need to have a PhD. And they do not necessarily have to be in the department. I think usually, I think the rule is the majority of your committee has to be in the department. So that would be, I think you have 4 people on your committee and your major advisor is 1. So 1 more needs to be from the department for sure. Most people have all of their committees in the department, but I really like to have my students have at least 1 non-department. So we have a lot of folks and so we have people in chemistry and a couple people in chemistry that are on committees. You can have someone who's not at BYU if they're like a PhD that works at a company that you're affiliated with, or even at another university. I think that's possible. Technically in the rules, there's maybe you need to work that out, in that circumstance. But I think it's possible. People have done that too. So it's a great question. Yeah, and your committee is kind of it's sort of up to you to have that be what you want out of it, right? So your committee is going to be there at your defenses, so your prospectus defense and your thesis defense. And if you never talk to them except for those times in your annual reviews, then it'll be what it is. But it's an opportunity for you to have people that are that you go to with questions, that there's more expertise. You can involve them in writing papers. It's sort of up to you and them how much you want to be involved with those people. So, great question. Okay, well, let's dive in. So I just, hopefully you have all of this already in your notes. I just wanted to get it up here so we can remind ourselves where we were last time. We're going to do, today will be our last day on shell balances for momentum. We'll start on shell balances for energy next time. So we had a quick overview of shell balances that we talked about, and then we started on this example of flow in a circular tube. We'll finish that in a couple of minutes, and then we'll work on flow in an annulus. So if you remember, in shell balances, the idea is that we took our geometry of interest and we're making a thin shell, and we do a momentum balance on that shell, right? And the idea is that we're combining, we're finally getting to a transport equation. We're getting there by doing a balance of this property, and we need the flux to be able to do that. So last time we identified our geometry, and in this case it was cylindrical, and we need to identify the direction of transport, right? So the momentum transport was in R, and we had the component, the Z component, so that was the tau RZ that we cared about, okay? And then we said, now we're going to do a balance on this. So we did a balance on a thin shell, and that's what we spent a little bit of our time on last time, right? We thought about areas and the flux through those areas, and we came up with flows, and then we wrote a steady state balance on that flow. And then, that gave us a bunch of things with delta R's and L's, and we divided and rearranged and took a limit as we went to delta R goes to 0, and out came this equation here, okay? Which was, a derivative of tau RZ related to pressures plus gravitational term, okay? And that's kind of where we got to, and I don't remember exactly what we wrote down last time because we were going to do it in class, but this is the point we got to, somewhere around here, right? And then we can go down to this equation right here by doing 2 things. One, we can substitute in Newton's law of viscosity, which is the relationship between the shear stress, right, and velocity gradients. And so that just gets plugged in here, all right? There's a minus sign that will come and flip the order of the pressures on the right-hand side, so that's where the minus sign went. okay? And then we introduced this dynamic pressure, and I don't remember if we said this last time or not, but this is basically just the pressure, and in this case, minus rho gz. And this is subtracting out the fluid statics part, right? So there's an actual pressure difference, right, between the top and the bottom, even when the fluid is fixed. And this dynamic pressure then sort of takes that part out. It allows us to kind of do two things. One, it allows us to pull this rho g into these pieces here, which makes our life easier, okay? And the other thing is that it allows us to think about this pressure as only the pressure part that comes from fluid flow and not from fluid statics, okay? So going from there to there, we get this equation. So this is our equation, okay? It's sort of 2/3 of the way, to being able to solve the math problem, okay? We have one more thing to do, and then we need to do the math. So that's just a kind of reminder where we're at. So step 4 in solving these problems is to identify boundary conditions, okay? And boundary conditions are, this is a boundary value problem, right? So this isn't, if you remember from math, we have differential equations, we have ordinary differential equations, we have initial value problems and boundary value problems. An initial value problem, you know all of the information at one point, right? So like you think about, usually get these in rate equations like in chemical kinetics, right? You know the initial concentrations of all the species. Or if you're doing a dynamics problem, you might know the initial position, the initial velocity of Newton's equation of motion, okay? In this case, we're going to know something about, this is distributed in space, so we're going to know things about, what the velocity is at different points in space in our geometry, okay? And there are a couple of different common boundary conditions, okay? The most common one probably is no slip, right? And no slip is a physical condition when you've got fluid near walls, okay? It's an empirical thing. There can be slip, but most of the time there's not. And so a velocity is equal to a constant on the boundary, okay? Where c is usually the velocity of the boundary. Okay, so in the case of a pipe here, if the pipe is standing still, then the velocity is just going to be 0, okay? But suppose maybe you had a pipe that was moving, okay, you can make it equal to the velocity of that pipe. It's a little bit silly to have a pipe moving because you just subtract that out and change your reference frame. But we have other cases where we'll have, say, on the parallel plate example, right? We've got one moving and the other stationary, and in that case, you've got no slip condition at the top and the bottom, one that's constant velocity, the other that's 0. Another common one is a constant stress condition. Okay, in the constant stress condition, you have something like this, tau r z equals to a constant. Okay, this is the case usually when you have boundaries between fluid layers. Okay, and often the case is you'll have this constant will be 0 when in contact with air. Okay, so what you're saying is that the stress has to be the same between these two different fluid layers, and of course air has a viscosity that's much less than, say, water, so if you have a free surface flow, usually you're assuming that at that boundary you've got no stress, okay, and the fluid can do what it wants at that, if that makes sense, right? That's a common condition. Another condition is a mirror symmetry condition, okay, or an anti-symmetry condition as well. Okay, so mirror symmetry would give you that the derivative of the velocity is equal to 0. Okay, so if I have some domain and I can take it and flip it over, okay, so that it has a mirror image, all right, it has to be an even function, and if it's an even function, I can tell that the first derivative has to be equal to 0 across that mirror boundary. Okay, if it's anti-symmetry, it means if I can flip over that mirror and it's upside down, then I know it's an odd function. And in the odd function case, I know that the VZ has to be 0 at that point, okay? So this is useful, for instance, if you're doing like a computational fluid dynamics simulation, and you've got some geometry, and you know that there are mirror symmetries. Instead of having to simulate the whole domain with, say, no slip on all the walls, you can use the mirror symmetry, and you can get only a part of the domain, and that'll allow you to do a simulation with less expense, right? And often it's also an easy condition to do, you know, when you're solving a problem, you know, you can use the derivative condition of 0, for instance. Okay? Another one that comes up fairly often is boundedness. Okay, and what you're saying there is VZ, the average or the absolute value of VZ has to be finite. Okay, it can't go into infinity. Or sometimes you might have the same thing on tau. The stress has to be bounded. Okay, and so one of the things in solving these problems that you're going to have to learn, all right, is you have to think about the condition you have here. So you look at this equation, and then you look at your geometry, and you have to sort of go through the mental list of these kinds of conditions and think about which might be appropriate. And hopefully you start to develop a little bit of an intuition about these, about what matters and what's going to happen to these equations as terms come out, and start to see which boundary conditions apply in which situation. So I don't know how to tell you more than that, like a formula for knowing that. I mean, like, for instance, this one is like always true, right? Like the velocity doesn't go to infinity. Sometimes it's a useful condition to use. Sometimes it's not useful. So, you know, you have to be careful about picking the ones that are, you have to make sure you know it's true, right? You can't pick a mirror symmetry condition if there's no mirror symmetry, but maybe that's the one that helps you get an answer. Maybe it's sort of redundant information, okay? And we'll see that here as we do a problem and as we do another problem, how to apply that, okay? So in this case, all right, maybe I'll pause and ask questions, because that sometimes when I know when I say things like that, it makes engineers a little nervous sometimes, right? Because you're like, oh, there's no easy formula, I'm gonna have to use my judgment. That makes it a little hard, okay? But we do enough examples, okay, that hopefully you'll see these cases. And then when you get, say, on an exam, it's not the end of the world, you haven't seen it, all of it before, right? I want to bring something crazy new on the exam, okay? Questions about boundary conditions? Okay, so in this case, if you think about the problem here, we're going to have no slip on the outer wall, okay? That one's probably the easiest one to get. So we'll write down, in this case here first. That's like a really ugly. So in this case, we've got VZ at R is equal to big R. So we said that that was this outer wall here. This is R equals big R out there. That one is going to equal 0. Right? So that's boundary condition 1. And then the other one that's going to be useful here is going to be VZ at R equals 0 is bounded. Okay, and we'll see why that's useful. So you might start out usually, okay, no slip is usually the one to try first, right? And but you need 2, because this is a second order differential equation. Okay, so you need 2 boundary conditions. So you start out and think no slip, that makes sense, okay? But as you look at this problem, you go, well, what else can I use? All right? There isn't like a mirror symmetry. There's rotational symmetry, but that wasn't one of our conditions. There's not some flat area you can flip it over. Okay, so that one didn't make sense. And constant stress doesn't make sense. You've got walls all around. Okay, so you're kind of sorry out of luck on those 2. So the only one that's left is this bounded case. Okay, and as you'll find in cylindrical coordinates, that's often useful. Okay, because we're going to find out that we've got the math here is going to give us things that blow up. And so we're going to see that we're going to need to say it's bounded to get rid of some of those constants. So that's where that's coming from. So some of that's a little bit of foreknowledge, but I'm trying to give you some intuition as to why as we're going here. All right, so now we're left in the last case here 5, which is math. Solve the boundary value problem. Okay, so now we have a fully posed differential equation, right? We have an equation and boundary conditions. From this point on, this is just pure math muscles at work, right? Everything that you took all those math classes for, now it applies. Okay, so in this case, we can rewrite it mu over r, d dr, r dz, dr equal to, and I'm going to write this as a delta p to save myself a little work, over L with these boundary conditions here, which we'll just put a check mark by, we'll rewrite it. Okay, so I'm going to give you 4 minutes, okay, 5 minutes. Integrate this one twice, okay? Don't apply the boundary conditions yet, but this is just a separate and integrate problem. Should be able to integrate that, all right? I think you'll be more awake than if I just do it by myself on the board, okay? So I'll give you a couple minutes head start, and then I'll start working it, and we'll see if you guys can get the thing I get. All right, you guys get what I got? Maybe I'll only give you 3 minutes. Give you a second to catch up to me. Still see some writing. That makes sense, Dan? See, we kind of
Yeah,
examine it.
I made a goof.
Made a goof? Which goof? If I can pick on you.
I didn't do the C1 over R, so I just had the R instead of L over R.
Yeah, you forgot the C1 here?
No, I had that.
You had that,
just
but then
when
you
I forgot
forgot
the
to-
R over,
So you had this one that got canceled, but you didn't have the one over?
so I
Yeah.
just ended up with C1 R instead
Yeah.
of C1.
Yeah. Yeah.
Gets you every time.
There you go. So you see why we're gonna need the boundedness one? You see where that's gonna come in, right? So let's think about the boundary conditions now, okay? So I plug these in. The boundedness one is the easiest one to see right away. So if we plug in 0 here, that term goes away, but this term goes to infinity, right? The log of 0 or negative infinity, okay? And so that's a problem. So in order to be bounded, C1 has to equal 0. And physically, if you think about what that means, right, when R goes to 0, that's at the center of the pipe. That says that I can't have infinitely fast flow in the center of the pipe, okay? So that would be an issue if our model predicted that. What's up?
So couldn't we also still use the mirror symmetry though, right in the middle? Because we know that.
I don't think it's mirror symmetry. So,
The R right in the middle, the dBzdr isn't changing, it's 0, because it's not changing.
yeah, I don't know, so in a flat plate, that's true. So, or if I have a flow in a rectangular duct, that's true. But in a circular thing, I don't have a mirror plane, right? So like I don't have this plane that gives me the same thing. And maybe if I do, it's not dBzdr then. I have to switch coordinate systems to be in Cartesian coordinates. And then I have a hard time. So you're right to think about that. I certainly have symmetries, right? But I think I have a rotational symmetry. I'm not sure the mirror plane is that easy. I think because of the fact if it's a reflection, I have to pick, say, an x-axis to reflect it out. And now I have to think about that derivative. That's what I think the answer is. But that's a great question. Any other questions like that? I like those questions because it shows you're not just like blindly accepting what I'm saying, right? You're thinking about what makes sense. Okay, so C10, so that guy's gone. Okay, so now we apply the other boundary condition, Vz of R equals big R. Okay, and we know that that has to equal 0. That was no slip. So we just plug big R in here. We got delta dynamic P over 4 mu L big R squared plus C2. So that's going to be really easy, right? We're going to get C2 is equal to minus that guy. So now we can plug that back in here. Or we'll just plug that in. And we get, let's see, where we have that expression. So I get Vz is equal to delta P over 4 mu L R squared minus sign comes because I put that over, delta dynamic P over 4 mu L big R squared. Okay, and we can write it a little nicer as delta dynamic P over 4 mu L. And I like to make things in dimensionless groupings, so we'll pull out an R squared, and we'll make a little r squared over big R squared minus 1. Okay, and that's our answer. Okay, sometimes the people pull the negative sign out here and flip this around, make this a 1 minus R squared, put a negative out here, because I think the pressure difference is usually negative, right? Because the PL is usually lower than P0 in pressure-driven flow, so you'll often see it written like this. Okay, 1 minus R squared over big R squared. Okay? So pipe flow, okay, hopefully we've seen that one before a lot. So there's a couple things to just sort of point out here about this. Erase a little bit. We'll do our other example. Okay, so here's some useful things you can calculate from this, and I think these may be on some homework problems. So you can calculate the shear stress. So in this case, right, you calculate minus mu dVz dr to calculate the shear stress. So we could come over here and look at our expression. Now we just have to take a derivative with respect to r. to get that guy out. So that's not too bad, right? We're just gonna multiply by 2, right? And get the R, this part goes away when we do that. So that one's pretty easy. I think it's minus delta P divided by 2LR. Is that right? Did I miss a big R in there? Shouldn't there be a, oh, the R squareds cancel. That's what happens, right? So I get the 2 cancels here, the big R squareds cancel. That, okay? So I can calculate an average velocity, right? The average velocity is, one way to think about it is it's the flow rate divided by the area. So how do you add up or how do you get the flow rate? You have to add up all the flow. So to do that, you do the double integral over the velocity, VZR, okay? You think about that, okay, I have to average over the R direction and the theta direction. And remember, in cylindrical coordinates, the Jacobian gives me this extra R term, right? So R d theta, okay? And then the area is the same integral, but with no velocity in it. So this one should go from, let's see, R should go from 0 to big R, and then 0 to 2 pi, 0 to big R, 0 to 2 pi. Okay, so if we want to calculate something like flow rate, you can just use the top. If you want to calculate the average velocity, you can divide these out. So we won't spend our time doing that integral. You can do that on your own, but this will give you the following: minus delta P R squared divided by A mu L. Okay, so that's the average velocity. You can also look at things like what's the maximum velocity. The maximum velocity occurs where the derivative equals 0, so you can set that equal to 0. That ends up being the center of the pipe, which is easy to find, right? That's where R equals 0. So then you can rewrite this, for instance. Sometimes this will be written in terms of the maximum velocity, which is, delta P over, or is that R equals 0, which is just this thing in the middle, in the front, right? So that they'll write things in terms of maximum velocity. And you can use this also, say, to calculate the mass flow rate. So the mass flow rate is rho VZ average, pi R squared. So I'm going to just write that out here, which you should be able to get, I think, really quickly from that guy. Delta P I R to the 4th over 8 mu L. Okay, so these are just some quantities you can calculate. These are in the book. But I wanted to sort of point out, once we know the velocity field, we can calculate anything we want from it, right? Might be a little bit of work to do some integrals, to do some derivatives, but we know everything at that point. Questions about flow in a tube?
I have a quick question.
All right.
Is there a reason that rho canceled out when we went from the mass flow?
Oh, did I just drop the row? Sorry. I just remembered. All right, so flow in an annulus. So an annulus is the following, if I can draw it. Right, we've got a pipe inside a pipe, okay? So now we want to look at what's the flow rate, or what's the flow profile here. Right, how does that look? Okay, and we can draw a similar thing. We can make this L. We can make RZ like this. We can make this direction R equals big R. And often the convention here is to make this one R equals kappa R. Okay? The reason they do that is instead of, oh, I just drawn the back of the chair, instead of having a second R, this kappa is the fraction, right? How far out are you? You know, we'll see that we have lots of ratios, then you can cancel out. You just get kappa left over. So that's the convention in this problem often. Okay? So I want you to think about for a minute, I want you to go through the first 3 steps here. Okay? Maybe talk to your neighbor. I know we're like social distance, but you can still hear each other. Okay? So, you know, steps 1 to 3, which were, I'll remind you, were the geometry, and there was the balance equation, okay, and then taking the limit, okay? And I want you to sit down and figure out what is the equation, the one that we started with today. You know, what's the analog of that for this problem here in the hands? Okay, so take 5 or 6 minutes and see if you can figure that out. All right, I will walk around and help you answer any questions you may have. So sit down, maybe get out a scrap piece of paper to sketch something if you don't want to improvise notes. But either way, spend a few minutes and look at that. So what do you think then, Tyler?
I'm a little bit confused. I'm just trying to think of how that equation looks different.
So in the 3 steps, what did we start out with in the geometry? So let's just think through those real quick. So the geometry, is that different or the same as before? When we talk about the geometry, we're talking about the direction of the transport, right? And which direction is momentum being transported?
So still along the R direction.
It's still in the R direction, that's right.
So
So it'll still be tau R something, right? And then which component is it? Like which velocity direction?
Z, the velocity.
Right, so it's still tau R Z, right? Okay, so 1 has to be the same, right? Okay, so then 2, and 2, that's where we did all these, we set up a shell, and we did these different pieces through the shell. So, you know, what does the shell look like here?
So it would look the same.
It would look the same, right? So that would mean if we have the exact same shell, we have the exact same thing, we should have the same balance equation, right?
Yeah.
So then if we take the limit, what are we going to get there?
It's just going to be the one as we approach the smallest.
Yeah, so this, right, in our shell, remember that this is our like overall geometry, but our shell geometry is like different. You can think of it as like being in the space. So the delta R in that of the shell is just whatever delta R we make up, right? So it's actually the exact same, right? That's a trick question. Now I told everybody. So, okay, yeah, of course. All right, so anybody wasn't listening to me talk to Tyler there?
I've said exactly the same.
Does that make sense, Gloria?
So the difference is just for delta R
The difference is what? I didn't hear you.
between shell and this delta R.
Yeah, so like a shell is just this geometry. This is great, okay? So the shell is just some geometry that we're drawing. Okay, it's a little confusing because it's kind of an annulus too, right? So this is our overall geometry. You can think of the shell as a thing we'll put inside our geometry at some point, right? And then we're going to take the limit as this delta R here. It's really tiny. So you can imagine just like a dotted line, you know. That's what our shell's going to look like, right? So our equation is sort of valid for that piece, okay? That differential chunk, right? Of what's flowing in and out, right? In and out, kind of that sort of thing, right? So that's how we're setting up the shell. So then, you know, when we apply the boundary conditions, right, we're saying we're going to apply the boundaries there, and our shell balance is good for all the points in between there, right? That's where we can write down our equation as a function of space. Yeah.
So I'm jumping again, but does that mean our boundary conditions are not going to probably use the boundedness this time?
That's exactly right. So we're going to have the same equation we had, right? We're going to have mu over r d dr r dz dr is equal to delta p over L. That's what we had before, right? But number 4, boundary conditions, okay? We can't use the boundedness. Remember, boundedness came in at 0, right? But that's not part of our flow regime anymore, right? There's something else in there. Maybe it's some other fluid, and that would be the same pipe flow problem we just did, right? If we're doing like a co-flow heat exchanger. Yeah,
I was gonna ask if we just had the 0 boundary condition, but twice on each side, so kappa R and R.
that's exactly right. So here we're going to have VZ at R equals big R equals 0, and VZ at R equals kappa R equals 0. Exactly. Okay, so we got no slip on the inside and no slip on the outside. Okay? So then, if we have the same equation, we have the same boundary conditions, we're over here now to math. Luckily, we have this already written, right? This part up to here is all the same, right? Just rewrite that one. Okay? Because taking the two integrals of that thing doesn't change at all. The thing that changes is applying the boundary conditions and finding those constants. Okay? So it's a little harder though, because this condition here means that this natural log term doesn't go away, right? So it's not quite as easy as the pipe flow case. So let's write it out here. So if I write VZ at big R, I'm going to get delta P over 4 mu L big R squared plus C1 log big R plus C2. When I write VZ at kappa R, I get delta P over 4 mu L kappa squared R squared plus C1 log kappa R plus C2. Okay? So I find in these situations when I am doing something like this, okay, when I apply my boundary conditions and none goes away really easily, often I try and subtract them or add them together, depending on whichever makes sense. Okay? So here, if I subtract, that'll make my life easy because C2 will go away, right? So, and I am going to, I don't want to do the algebra out. I want to tell you about, set up this other problem that I'm going to just give you the notes for. So I'm just going to tell you what these end up being. So C1, you can do the math. This is often actually the messiest part of these problems. okay? As long as you don't screw up the, you know, I don't mean that to be insulting, I screw it up all the time, but if you screw up this, then you end up having boundary conditions that make no sense, okay? Or like that you apply, you get an answer that makes no sense. So that's one place you make a mistake. But the most common place is that you just have algebra sort of applying to these constants. But when you end up here with this, C1 is equal to delta P divided by 4 mu L, and you get this 1 minus kappa squared divided by the natural log of 1 over kappa. Okay? So now you get this extra chunk over here. I guess it was C2 before that we had that was decent, but you get this piece. And then for C2, you get minus delta P over 4 mu L r squared times 1 minus, and then this same chunk, 1 minus kappa squared divided by the log of 1 over kappa multiplied by the natural log of r. I want to be close on the put a square brace there. Okay? So you get C1 and C2. Then you take those guys, plug them back in, and I'll write it out down here. So we found that out, minus delta P divided by 4 mu L. So r squared out front. 1 minus little r squared over big R squared minus 1 minus kappa squared divided by the log of 1 over kappa, natural log of big R over little r. Okay. That's the final answer. Try to write that down. Okay, so for this one, we just have 4 minutes or so to talk about this. So I'm just going to show you the setup to it, okay? And then I'll post my notes on this problem because it's messy algebraically, okay? So this example, suppose I have a pipe and I have mass in there, a cylindrical mass, okay, of some kind that has size h, okay, and I can call that kappa r, and that one r. All right, and if I let this guy go, and it starts falling, and eventually it'll reach a terminal velocity. And it turns out I can use that to calculate the viscosity. Okay, so this is a falling cylinder viscometer, okay, appropriately named, right, for all of these. Okay, so, so this problem is a lot like the annulus problem that we just had, except we've added a part where now we have to do a terminal velocity problem. Okay, so I don't know if you remember doing terminal velocity problems from before, but what we're going to have to do is this is going to fall, right? And so now we're going to know that there's no slip on that wall, but our boundary condition on this wall is going to be that it's moving with the velocity, okay? And that velocity is the terminal velocity. And that's kind of hard because that's self-consistent with the fact that, like, what is the terminal velocity? Well, it depends on what the flow rate is to tell us what the terminal velocity is. Okay, so that makes our life a little hard. Okay, so I'm just going to remind us a little bit about these terminal velocity problems. And I can do something in 2 minutes that gives us the form of the answer without one piece. And then you can spend 9 more pages on the last piece. Okay, so that's what you can look at the notes. So we look at terminal velocity. If you remember, we set up these balances, F buoyancy plus F gravity plus F drag, okay? And so we're writing a force balance on this guy right here, right, on the cylinder. And we say, well, the buoyancy force, this is going to be rho of the liquid times G times the volume, okay? And this gravity is going to be rho of the object times gravity times volume, okay? And the drag force, if you remember, we said a drag force was equal to 1/2 rho u squared drag coefficient times the perpendicular direction, a perpendicular, okay? And in this case, we have, let me just write this out. So I'm gonna write out 0 is equal to, we have rho, this gravity is downward. So that's gonna be minus n. So rho L minus rho 0, gravity times pi kappa r squared times the height, right? So that's the buoyancy minus gravity, okay? And then the drag force, if you remember, the drag coefficient was a constant at high Reynolds number. Remember this Reynolds number much greater than 1, okay? But it goes like some constant divided by the Reynolds number at low Reynolds number, okay? And so for laminar flow here, and I guess this one's actually not 1, it's 10 to the 2. Okay, so we're going to make a guess that this is the right case, all right? And it turns out, you can look at my notes more for this, that I can rewrite this as 1/2 rho u squared constant divided by the Reynolds number. And when you think about the drag coefficient, we talked about these in fluids. What we're really going to care about here is actually the length of this cylinder when I'm doing low Reynolds number drag. And it looks a lot like a flat plate. So we're actually going to use a parallel. Okay? I'm allowed to do this because I'm going fast. This is probably a confusing one. Okay, this is going to give me mu u h times kappa when I put that all in. Okay, I'm skipping the algebra. So I can put these pieces all together. So this is going to be plus a drag. That's my drag right there. And I'll just write this sort of final piece up here. If I do that, notice I can solve for viscosity. All right? So if I solve for viscosity, I get rho 0 minus rho L G kappa r squared divided by u. And I was kind of fast and loose. U here, that's the terminal velocity. Okay? U. And then I'm going to have something over here that is a function of kappa. Okay? In this case, I get 2 over C1 kappa. Okay? And now what you'll see in the notes, sorry I took an extra minute of your time, but what you'll see in the notes is that we can go through the same process, okay, for solving the flow in an annulus. And there's an extra trick because you have to solve for the terminal velocity. So instead of having two unknowns, C1 and C2, you have C1, C2, and U, the terminal velocity. And you have to use the mass flow rate to calculate that. And it's pain, so we're not doing it in class, okay? But it's an extra example you can look at, okay? And you end up finding then the viscosity, which is this same chunk multiplied by a more complicated function of kappa, which basically is a function of the geometry, right? So this was just a quick and dirty way to help you see the big picture of that problem, okay? But you can go through and follow all the dirty details of the math, you know. facilitate, no, I forgot date, you want to press friend, right? Yeah. Okay? So, there you go. We'll do energy next time. Fewer factors. Thanks for giving me the extra 3 minutes.